In this chapter, we will look at variables in tires and losses of energy in a rolling tire. To conquer both speed and distance, you should train with lots of persistence. The tires you choose from the list you peruse should have a low rolling resistance. When we look at the rolling resistance of tires, which is really a very complicated issue, then we can think of a number of variables. The rolling resistance is a function of all of these things: the type of rubber, the casing, the thread count, the tire shape and width, type of inner tube, aerodynamic drag, friction, tire and tube deformation, tire pressure, and bumps. If you look in the literature, you'll see a number of different ways that this topic of rolling resistance is considered, and some people do not include aerodynamic drag, but this is the list I'm going to use. I'd like to divide this list up into two groups. The first group here is the variables in choices of tires to use, and it behooves you to do quite a bit of research because it's a very involved topic. But then once you've made your choice, we want to look at the effect on those tires of aerodynamic drag, friction, tire and tube deformation, tire pressure, and bumps. So we will look at these five here as the causes of the loss of energy in a rolling tire. But you'll see that tire pressure is absorbed and included in the discussion of several of the other categories. So we'll really look at four different categories, starting with aerodynamic drag. Here's our bicycle. The wind is coming toward the bicycle from the right, and we're going to expand that area there to look at two different wheels with different shape and widths of tires, and now look specifically at those areas there and get a close-up of what that looks like. We will consider the cross-section of the tires to be half circles. And we want to look at the drag caused by the tires from the air coming from the right. Once again, consulting Dave Wilson's book, Bicycle Science, we can look at some drag coefficients in two dimensions. This one here is a closed half cylinder with a drag coefficient of 1.16. Now, obviously, if I turn that graphic for the half cylinder around, I have the same thing, but now it looks like my graphic. And I have inserted the values for the drag coefficients. And let's move them apart to create a little bit more room. These graphics show the riders coming towards us. This represents the narrower tire, and the wider tire here, we'll call that area A1, this area A2. Obviously, the area of A2 is greater than the area of A1, and the drag coefficient is the same in both cases, so that the product of the drag coefficient times A2 is greater than the product of the drag coefficient times A1. We're going to calculate the power necessary to overcome aerodynamic tire drag, and we can get that from this reference down here. The power is equal to 1/2 the drag coefficient times the frontal area times the density of air times velocity cubed. We can figure out the values of some of the unknowns in this equation. For example, with A1, the frontal area is going to be the product of the width, 23 millimeters, times the diameter, 630 millimeters. If I work that out, I get 0.014 square meters. And in the second case, the frontal area is the width times the diameter again. That comes out to 0.018 square meters. The density of air at 20 degrees centigrade at 1 atmosphere of pressure, or sea level, is 1.3 kilograms per cubic meter, and our velocity is 20 miles per hour, or 8.9 meters per second. When I multiply that out, I get the power is equal to this expression. And when I multiply that through, I get 7.4 kilogram meter squared per second cubed. And that is actually the definition of a watt. So I have 7.4 watts. And the second case, when I multiply that out, 9.6 kilogram meter squared per second cubed, and that is 9.6 watts. This, by the way, is a great illustration of the beauty of the SI system. I expect my computation for power to yield watts, and if I get the units right, which I did, I have confidence that I probably did the calculation correctly. At a speed of 20 miles an hour, or 8.9 meters per second, the power needed to overcome aerodynamic drag is 7.4 watts for the narrower tire and 9.6 watts for the wider tire. If the only thing I had to think about was aerodynamic drag, I would always pick the narrowest tire, but there are other things at play also. I think quite obviously this is not a very precise calculation, but it does show us how some of these variables play together. But for one thing, we're not taking into account here the interface between the tire and the rim. So a better match of the tire with the rim width will probably result in less aerodynamic drag than a poorer fit. Next is friction, and specifically friction between the tire and the road surface. In the earlier chapter on friction, we looked at the intermolecular attraction between asperities in the tire and asperities in the road surface. And we talked about how these intermolecular attractions have to be constantly broken and reformed as the tire rolls. But this is not energy neutral, and there is a slight but steady loss of energy in the form of heat in the constant breaking and forming of bonds between the tire and the road. Next is tire and tube deformation. Very quickly, here we see a tire and a tube. This is a hook bead system, and it's a clincher. There is the rim tape, the rim hook, the tire bead, and over here I have a rim that I've inserted a tube in, and I've inflated the tube. Let's imagine our wheel and tire, and if you look at the 3 o'clock position, you'll see a rectangle, and let's say that we're looking at the rim, tire, and tube combination at that point. We want to see what happens to the shape of the tire and tube as the wheel rotates clockwise 1/2 turn, and as it does, the tire and tube go through the load-bearing zone. We can visualize this. In the load-bearing zone, there is a force from gravity pulling the mass of the bike down, and that is countered by the normal force of the road pushing up. This causes a deformation of the tire and tube as it goes through the load-bearing zone. This deformation and reformation of the shape of the tire and tube happens continuously and thousands of times in a bicycle ride. There is a loss of energy due to something called hysteresis, and I'm going to give you a quote from the National Academy of Science. Hysteresis is a characteristic of a deformable material such that the energy of deformation is greater than the energy of recovery. The rubber compound in a tire exhibits hysteresis. As the tire rotates under the weight of the bicycle, it experiences repeated cycles of deformation and recovery, and it dissipates the hysteresis energy loss as heat. Hysteresis is the main cause of energy loss associated with rolling resistance. You can think of the heat loss as being due to the friction between the tire and the tube. In an earlier chapter, I showed you some graphics where we compared tires of the same width but different pressures. And we saw that for these two tires, the same width but different pressures, the tire on the left with 80 pounds per square inch of pressure, the one on the right 120 pounds per square inch of pressure, we found that the tire on the left had a wider and longer contact patch than the tire on the right. Now let's change that to a different comparison, to one of comparing the same tire pressures but different widths. Here we see the contact patch areas in comparison. The narrower tire on the left has a longer and narrower contact patch than the wider tire on the right at the same pressure has a shorter and wider contact patch. Now, I will give you what I will call the prevailing theory about this, which is the following: that the wider tire will have less rolling resistance because there will be less vertical lift to surmount the bumps, because the tire will absorb some of those. There will also be less friction between the tube and the tire. The combination of those will give us less hysteresis loss of energy in the form of heat. Next is bumps. Consider a tire made of a hard, inflexible rubber, and it's rolling along and about to encounter a bump. Let's watch as the wheel goes up and over and down the other side of the bump. Now let's look at the energy changes that just took place. I know that most of the weight of the rider on the bike is on the rear wheel and somewhat less on the front. If I have a combined weight of the bike and rider of 220 pounds, that is a mass of 100 kilograms, and let's say I have 60 kilograms on the rear wheel and 40 on the front. At this point, my wheel, and more importantly my bicycle, only has kinetic energy of motion. But at the top of the bump, some of that kinetic energy has been converted to potential energy according to this formula here: mass times the force of gravity times the height. And if I put in some information here, 40 kilograms, the acceleration due to gravity, and let's say I have a bump of 1 centimeter, which would be 10 millimeters or 0.010 meters, then I get 3.92 joules. At the other side of the bump, I have converted potential energy back into kinetic energy, and I should get back the same amount, which is 3.92 joules. But in reality, there's a loss of energy, because whereas I convert kinetic energy to potential energy and then potential energy back to kinetic energy, I might get 3.92 joules that I have to put in to get over the bump to the top of the bump, but maybe going down the bump I get a little bit less back. Now let's put that in perspective. Let's say I have a rider, total weight of bike and rider of 100 kilograms, riding at 20 miles an hour, which is 8.94 meters per second. If I use my equation for the total kinetic energy of the bike, I'll find out that the total kinetic energy is 4.04 times 10 to the third joules, or let's just call that 4,040 joules. Whereas the energy of my front wheel to get over the bump, to go up it and over it, is more like about 4 joules each way, losing a little bit on the downside. But I have to do this thousands of times when I ride the bike. And I don't feel this because some of the energy is taken up by the tire, but there's a loss of energy there too. And as a consequence, once again, I see a loss of energy due to heat in the form of hysteresis. One interesting and unique situation is the following, where you have an indoor wooden track that's perfectly smooth and sanded, it's varnished, and it's also vacuumed. So for that, I'm going to use a totally different kind of a tire. Here's a tubular track tire. It's intended only for track riding. Because the track is perfectly smooth, there are no bumps or other irregularities dealing with the track. I have a slick tread on the tire, a very narrow tire, only 19 millimeters, and I pump it up to a whopping 220 psi. The combination of all of this gives us very little tire deformation and hysteresis loss. Both of those are minimized. In this very broad concept of rolling resistance, however you want to define it and whatever you want to include in it, there are certainly many variables. And lots of very good scientific testing has been done, but only a couple of factors can be studied at one time. There are just too many variables to simultaneously consider all of them. Which means that for you, for a specific ride under a specific situation, specific bike and so on, you really have to do your own empirical testing, vary some of these factors, and see what gives you the best results. Unless we want to use the unifying equation I've come up with, and that comes from combining a knowledge of physics with chemistry, engineering, fluid dynamics, mathematics, relativity, ancient Greece, and English poetry. After combining all of these, we come up with the tire with the lowest coefficient of rolling resistance. Using this equation, I have come up with the best tire for this elite time trialist to use, so that he will be assured of winning a gold medal in the Olympics, the World Championships, and the Tour de France. So here it is, the scientifically and mathematically determined optimal time trial tire. Maybe I better check that unifying equation again. Back to something a little bit more serious and looking at the complexity of determining rolling resistance. You might reasonably assume that surely there have to be internationally agreed standards for measuring rolling resistance, so there is a scientific basis for comparing different tires. There are no such standards, but there is hope because ASTM International has taken this on as a project. I am a member of ASTM and I'm on the relevant committee.